This is track 3, lower layers, and the talk would be on how the analysis of electrical current consumption of embedded systems could lead to code reversing. The talk would be given by Yann, Allain, and Julien Moinard. So guys, take it from here.
So, thanks for coming to this hardware hacking style session. This is the agenda. We will go through it through the session. Where we are? We are from France. Is there any French people in the room? Thanks for coming to support us. And you can translate the QA at the end if we don't understand. Okay. So we work in a small business company dedicated to IT security and to embedded security system. I'm Yann Allain. I'm the CEO of Opal Security. And I was the former CSO application security officer for a big hotel company. I don't want to say the name. And this is Julien Moinard, which is a specialist, an electronic specialist. And why? Because this session is oriented on some way we can find some method to extract the code on an embedded system through electronic analysis of the power consumption. Just to begin, I need to know who has basic knowledge in electronic. Can you raise your hand if you know what is a transistor, what is a resistance, etc. So you can go away in a part of the session because there is a lot of things to explain to IT security guys only. So what's the research context and what is our goals? We do several embedded system audits. Our customer asks to do that, but sometimes they don't let us to open the box. Don't ask me why, but they don't want. It's all about this research. It's all about to find a way to access inside the code inside the embedded system without the need to open it. Okay. But basically, approach regarding embedded system audits is going to find a way through IP connection, web interfaces, TCP services, and the auditor normally try to access the Ethernet ports. This is the most popular way to pen test or to audit an embedded system in a black box mode. Of course, auditor could try to open the box. You need to some time to defeat some anti-tampering system. Normally, anti-tampering system is used on cryptographic system or POS, or payment terminal. You can tear down. You try to access electronic circuits, and you are trying to dumping firmware and to analyze it just to find vulnerability in the code. But on all embedded system we use, or you use, I don't know, there is always another existing connector, the power line connectors. As a security auditor, may we use this access to do something? In fact, this is our goal. We want to extract the code executed on the embedded system from its current consumption. It's similar to say from the power connector. We don't talk here on the electric plug on the wall. We just want to use these connectors. Okay. This is a low-level voltage connector, not the 110 voltage in USA or 220 in Europe. How we can achieve to grab the code with our methods? We have a wish list. We want to be pragmatic, keep it simple as possible. We don't want to use no mathematics and complex stuff. It's not for us. Even if we are all electronic engineers, we don't want to use mathematical formulae. We want a cheap approach, and we don't want to reinvent the wheel. Is there an existing research on this area? Yes, many. I don't know if you can see at the back the number Google sent to us with a typical analysis, power analysis method to extract some keys, but there is 4 million results. But all this paper mainly focus on extracting only the cipher keys. They only want to take the keys outside the box and to be able to decrypt whatever you want to decrypt with the keys. We want more than cipher keys. We want to extract the code via a power analysis method. In fact, we are looking for instruction and data without opening the box. We make we make a research in internet. There is few papers related to code extraction via power analysis. We only find 3 papers. You have the link here. The first one is very cool, but the researcher only focus on finding instruction. He don't want to try to grab the data. As a security auditor, we want to try all the data and the instruction. But it's a very great paper. I think it's the first guy who tried to make a sort of disassembler of our electricity through his method. The second one is have some chapter dedicated to our goals to extract the code. But this is a gouv.fr URL, and this is close to military domain, not military but sensitive domain. And in this paper, they show us that they can do something, but they don't show us how exactly they do the thing. I don't know why they published the paper. And the third is too specific for our goals, because our goal is only focusing on embedded system based on microcontroller of FPGA. We don't want to extract the code from Java card, because our customers don't use Java card for now. The main problem we face with this publication is that they are full of mathematical formulae. I don't know for you, but for me, I don't understand the equation. Anybody can help us? And for me, I don't understand the title. Inference of circuit by current analysis by correlation. I'm not sure to be able to understand what is a correlation, an inference. Don't know. It's not for us. It's not for you? Okay. So, we want to extract the code. How? We begin with a question with this research. What is the link between the power consumption and instruction and data executed at hardware level? What is the link? In fact, for all electronic engineers here, there are many, I think, a fundamental and basic electronic component is the answer. Used everywhere. Please, gentlemen, welcome to our friend, the transistors. There is many transistors in every embedded system circuits, inside the FPGA, inside the microcontroller. Now, how we can extract the code from transistor? So we need to come back to some physical basic knowledge in electronics. A microcontroller is composed, an embedded system could be composed of microcontroller, and a microcontroller is composed of several basic functions. You have memories, ALU, timer, serial interface, I/O bus, etc. Each of these functions are designed at electronic level with transistors. For example, if we take just for example an AND function, at the logical view, this is the function. Maybe at the back you can say that, but it's just an AND function. At the electronic view, at the design view with transistor, non-function is we only use 4 transistors. Okay. Of course, at the physical view, you have at the bottom right. Yes, bottom right. You have the signal on our oscilloscope. What you must know is when a transistor processes a bit. In fact, it doesn't process a bit; it processes voltage and current. But a voltage could be the equivalent of a bit. 5 volts is 1. 0 volt is 0 in binary. So when a transistor processes a bit at physical level, it commutes. In fact, a transistor could be used like a switch, a digital switch. When a transistor commutes, there is a current peak. This current peak is arising at each transition. Okay, let's see in the lab what's going on in transistor. This is our hardware stuff. We make just some graphic for you with 1 transistor, the black in the breadboards. For each transition, there is a clock signal with transition from 1 to 0, 0 to 1, 1 to 0, etc. There is a peak. This is the current peak we measure. If you zoom in, you can say that the peak is could be twice as large in amplitude as the clock signal. So our first experiment is with more 1 transistor. In microcontroller and FPGA, you have plenty of transistors. Microcontroller circuit implements more than 100 kilo of to 10 million. I don't know if it's exactly the figures, but you have plenty of transistors in it, in the circuit, in the electronic circuit on the wafer. Each time a transistor processes a bit, there is a current peak for each transistor. All transistors are linked to the power line. We need to make a power connection to all transistors to work. And all current peaks will be sent to the power line due to physical law regarding current inside electronic connection. Okay? We use this physical feature. There is no patch for this. This is the physical world. We can't apply a patch. To link the power consumption with bit processor. So, now Julien will explain in a more detailed way how we made our proof of concept. D'accord? D'accord. Okay. The French word. And I will stay just before. Good luck.
Hello everybody, thank you. I'm going to talk about a proof of concept, soft part and hard part. So, how to move from one grabbed, step 1, and in step 2, data and instructions code with our approach. We have designed a proof of concept tool to analyze the electrical current conceptions for embedded system, to extract the code, execute. We need to acquire more bits, not only 1 bit. For instructions, a lot of bits via current conceptions. It is a very hard task, but how acquiring current conceptions? We need an embedded system, of course. Here, I use a microcontroller of microchip, and I need an Agilent oscilloscope. It's good oscilloscope for acquiring current conceptions. I need a programmer debugger for program the target embedded system, so microcontroller. We need a current probe. Yes, of course. We want to analyze the current conceptions. For this, we have a current probe. We have 2 solutions. A very expensive professional tool magnetic or electromagnetic current probe, but it's more expensive, more $400 each. Or a simple resistor, which costs less than $1. We choose a resistor, of course. We need a bit of software for help to tracking current conceptions. We make a homemade code with VB.NET used to control the oscilloscope. The code uses a standard library protocol, Visa.com. It's a free library that lets communicate with Agilent oscilloscope with a set of easy commands. For example, get data measurement, launch voltage acquisitions or current acquisition with probe, and send numerical value, digital value, to PC for analyze the current. In my software, I use a graphical unit interface for help to use this software with only one button for each steps. Our acquisition chain looks like that. We need embedded systems and a resistor embedded system and a resistor current probe. The oscilloscope for measure currents via resistor, and the PC catch the digital value of oscilloscope. So in practice, it looks like that. How we proceed to grab the current and extract the code. Step 1, I send a dummy code to microcontroller. PC1, in manufacturer or on another way. With the programmer, I send a code to embedded systems. And embedded system is ready to use for work in your car or your homemade on your computer, maybe. Step 2, in lab, embedded system 2, but with a current probe, resistor, and a probe is a probe for oscilloscope. The current conceptions sent to oscilloscope, not exactly. Oscilloscope measure current conceptions, and digital value sent to PC2 in lab machine and this PC2 use our tool, try to find instructions and data executed from the current conception on embedded systems. Our experiments. First steps, does the code really impact the power conceptions? In second step, do a move FF and move 0 lead to measurable difference in power analysis. Move FF is instruction used all the time on microcontroller. Is only one example. Third step, why microcontroller instructions pipeline impact the current conceptions. Pipeline, in next slide I explain what's this. And how overcome pipeline issues for our goals. And finally, could we create a disassembler over electricity? Is the goals. Does the code really impact the power conceptions? First result, we have a current conceptions related with NOP instructions. So on the left, we can see a code on microcontroller with for NOPs. NOPs is instructions, no operations. Is coding with only 0, is very basic instructions. It's here for lose a time on a program. On the right, we can see 4 NOPs with a peak of current with a transistor, and these 2 instructions, it's for synchronization instructions, is not the problem here. We can see in green the clock, and each edge of clock we have a peak of currents. So, some value of measurement, max variations of current is around the 0.1 milliamp. It's very low level of variations, and it's very difficult to catch this. But we have a good oscilloscope, expensive oscilloscope, and I can do something. Do a move FF and move 0 lead to measurable difference in power analysis. Experiment 2. To limit impact of parasites, our system takes a differential analysis and average measurement by oscilloscope. It's very simple. By oscilloscope, take average around 200 average, and it's very good for me. At first time, we measure the difference between current conception of 4 NOPs is a reference for the next slide, because 4 NOPs is no operation and make nothing, and eliminate a parasite. And second time, we measure a difference between a current conception with 4 NOPs, 2, and a current conception move 0, 0 with 3 NOPs. So we can make a difference between a move FF and move 0. Result 2. Current trace relate to move FF. We have 3 NOPs with, for example, move instructions with FF. I use my software and push only one button, capture current and show graphical difference. And I see a 2 peak of currents is the difference on 4 NOPs and only 3 NOPs with move instructions. We can see the difference. So, a current trace with a move 0 is the same. 4 NOPs with a move 0, we have 2 peaks of current. But it's not the same. Why? Why not the same? The instructions is different. We have a correlation between different value of data and amplitude of current conceptions. With a move 0, we have only 3 1 to encoding instructions on a microcontroller embedded system. And for move FF, we have only 3 1 for encoding instructions, but we have a data FF, so 8-bit to 1, so 3 and 8-bit. We have a more peak of currents. In fact, the current value measured depends on Hamming wave. What's the Hamming wave? Example. With data with 24, we can see in binary representation only 2 1 for encoding 24. So it's easy. 2 1 Hamming group is 2. But we have another instructions, another data with 2 1. We have 28 data with 2 1, and is our limits. So, for example, a multiply instructions is encoding with only 1. And the subtract instructions is encoding only 1, but not in the same place, of course. But instruction Hamming way is 1. Move literal instructions have 3 1, and the set instructions have 3 1 2. The two instructions have the same Hamming way. Some instructions have the same Hamming way. We have a collision. So we aren't able to difference move instructions and set instructions. For example, it's a limit of our analyze. Why microcontroller instructions pipeline impact the current conceptions? Back to the current graph. We have two graphs with two instructions, the same instructions, but data is different. But why we have two overshoots of currents when the code only have one instruction modifications? Why? So, because there is a decoding instructions pipeline inside the microcontroller is designed. Pipeline is designed to speed up the instructions decoding process. Pipeline are used by almost microcontroller manufacturer, and 4 steps for decoding instructions. And so the conclusions, a pipeline is not our friends, because the current conceptions of next instructions depend on previous instructions. And so very hard to analyze this. But how to overcome pipeline issues for our goals? We have solutions. The main idea is used the principle of pre-calculate hash table. The idea is to memorize a signature of electricity conceptions of each couple of instructions, pair of consecutive instructions, in an exhaustive way. The idea is to create a sort of dictionary. We can now compare the current conception of any instruction sent on the microcontroller, execute, and a dictionary. For generation of dictionary, I use a lab machine, a sample PC. I send a code with a couple instructions with different Hamming way. For example, instruction move 0, move instructions with data to 1 is Hamming way 1, but the Hamming way 2 and 4 is the same Hamming way. Don't program the microcontroller with this data, but the move 3 is necessary because I have a different Hamming way. We have 8 Hamming way. The program by programmer sent to embedded system with the probe. The current conceptions is measured for each pair of instructions and sent to oscilloscope. The digital value sent to our tools with library communication. On the software, we push only one button, and the result is saved to a file on a PC. And again, for 8 Hamming way, for this example, only 8 solution. So, only one button. Could we create a sort of disassembler of electricity? We will try to find instruction and data. On PC1, we send to microcontroller a program with a move 57 data. 3 nops with move instructions. I program the microcontroller and send it. And with another PC, I launch my software and I use the software and push the button file instructions too. And away result of hacking process with our tools. I push the button and perfect, because the Hemingway is 5, but it's not necessary here. But instruction 1 is move, and data possible is on the list, and I can see a 57 data. So I see a video. Comment on passe de l'autre côté?
We are electronic engineer without knowledge in IT.
So, another example. With a move instructions with 0 data, a sample instructions, move instructions, 3 nops. We try to find a move 0 instructions by the software. So I write the code and send the code to microcontroller with the button. And where microcontroller has been programmed and executes the program. I launch my software, push the button, and we can see the result. Perfect. The move instructions with 0 is see on the first line, 0, 0, 0. Way aiming is 0. Move instructions, move. Data, 0. We have a 100% of result. So we can try with another instructions. For example, a move with FF data. I send the program to microcontroller and wait for program the microcontroller. I launch my software. Push the button again, it's easy. So, we can see the result. A move instructions with FF data was found by the software. 100% of result for 2 instructions. But we have a limit, the Hemingway. Because we have 28 solutions for Hemingway 5. Last try, a move with 57 data. As the same, send the program to microcontroller. This program, finish. So, and the software find for the last time a result. It's the same result, but so we have move instructions, and on the list we have a 57 data. Is perfect, but you can see a lot of results on this list, and it's the limit of our analysis. But instructions with zero data have some % of result, and so result and limits.
So, thank you, Julien. We think it's pretty interesting to just measure a current to find an instruction. I don't know if you share this idea. No? Yeah? It's pretty cool for us, because we can go here without paying any briefing tax. So, what is the results? We succeed to extract parts of the code with current consumption analysis, and our approach seems to be validated with our proof of concept. However, we have several limits. First, Julien just said that there is a limit according to the Allain weights of instructions. So we have a lot of collision of instruction with our method. We have some issues also regarding some specific set of instruction. For example, some instruction on microcontroller have more than one clock cycle. So we didn't find a way for the moment, because it's in progress research. We didn't find a way how to manipulate this specific instruction. There is another drawback with our method, because we need to use a dictionary. We need to find a way to pre-calculate all the current graph. So our approach only could work with development boards, well-known development boards such as Arduino or whatever you want, or more professional development board from Texas Instruments, etc. Because we need to create the dictionary as a reference. Okay? So it's a limit. That's life. What we are going to do in further research, for the moment, we base our approach only on current amplitude measurements. Maybe we could add a temporal dimension of measurements. With this temporal dimension, we can spot when the transistor commutes in the signal, and we will be able to make a sort of distinction between bits that are set to 1 or set to 0 with the temporal dimension. We didn't try it for the moment. We will try it for the next black hat, perhaps. I don't know. Another perspective, from another prospective point of view, actually we use resistors. We can use some electromagnetic wave probe to ability to plug in the power connector our resistor. It's just to have more ability to check the code, to extract the code in an easiest way. As we are security guys, and we need to find some solution to mitigate the risk. There is plenty of way to limit this risk, but we just want to spot two because it's very simple to implement. As a designer of microcontrollers or embedded system at electronic level, to limit this risk, this is an information leakage risk, you can create a complementary current consumption via software or hardware to hide the true power consumption. In fact, on the left graph, you have the original power consumption of our embedded system that we are audited, for example. If we create a complementary electronic design that do the exact opposite transition of the first one, You have, in fact, if you make a sort of sum of power consumption on the left and the right, you have a power consumption with not so much variation. So as our tool need to check the variation to make decision, if there is less variation, we can't extract the code. This is a possible solution to limit the risk. At the manufacturer level, the guy who make the microcontroller, they need to be careful when designing the instruction encoding table. The more you have instruction in a naming white, the more it's difficult for us to extract the instruction without 100% success. If all the instruction could be encoded in a naming white, we have no way to distinguish them with our approach. So I will try to encourage my customer or your customer to make some slightly different design at electronic level to overcome this issue. What time? Cool. As a conclusion, we will say that, does the code really impact the power consumption? I will say yes. Do the different instructions and data could be retrieved via power analysis? I say yes, or we say yes. Could we create a sort of disassembler over electricity through the power line? We may say yes, but with the limit we just discussed before. For the moment, we can't tell you that it's possible to make an IDA plugins, an hardware IDA plugins to grab the code with this power analysis. For the moment, but we need to find some solution to overcome some issue we have with our approach. There are some figures about money. Julien needs a super oscilloscope to do his job. At the first time, we will try to use a USB oscilloscope with cheaper bandwidth. Don't try this. Use a big oscilloscope. So it's the maximum amount of money we spent. This study take 4 months to be finished. And of course, as I'm an attendee at Black Hat since 2001, we deliver to the community. We giving back the money to the community because the community helped us to do some security stuff for more than 15 years. So our code is open source. Use it. Download it. I think it's on the CD. I didn't check. Someone has checked? No? But it should be on the CD of Black Hat. You can improve it. If you make a significant improvement, please send us the updates. Okay? Just to be sure we have the last version. If you have, this is the end of our talk. I think we are on time because this is the lunchtime. And for French, the lunchtime is very important. If you have any question, remain at your disposal at the desk, or if you have any question before the lunch, you can ask in this room. Okay? Thanks for coming.
Thank you.